Welcome back everyone, Tom McNamara here again for our course in college algebra. In this video we are going to be discussing applications of linear equations. So in other words, we are going to start with a realistic situation and apply some logical thinking and mathematics to gain additional information. So the basic strategy when I'm dealing with applied problems, some people call them story problems or word problems. I'm looking to translate as much as I can into mathematical language. I'm looking for relationships between quantities because this is how I get my equations. How are two things related? If one quantity is 3 more than another, then I know I have something with a plus 3 in there, right? So that's what I'm talking about when I say look for relationships, and then I'm going to solve my equation. So let's get right into some examples here. So this first example is going to deal with money. Okay, so the problem reads, Kia borrowed money from her father at 5% simple interest to help pay her tuition at Wellington Community College. At the end of 1 year, she owed a total of $1,365. How much did she borrow? Okay, so let's kind of summarize everything here. Borrowed money at, what was the percentage? 5% simple interest. And she owes $1,365 at year's end, and the question is how much did she borrow? Question mark. Okay, so she borrowed money at 5% simple interest. This is how much she ends up owing. The question is asking how much did she borrow? So let's think about how this works here. You borrow some money. The person you're borrowing it from is going to charge you interest typically, right? So you're going to have to pay back all you initially borrowed plus a certain percentage. Okay, so we're going to let X stand for the unknown amount that this person borrowed. Now you might say, okay, we take 5% of X, and that's the amount she owes. Well, that's not really true, right? She has to pay back all that she initially borrowed plus an additional 5%. So she has to pay back 100% plus an additional 5%. In other words, she has to pay back 105%. Okay? So the amount that she would owe, relating it back to the amount borrowed, is this. Right? That's the decimal version of 105%, right? So you remember this. If you are converting from percent notation to decimal, you move your decimal point 2 spots to the left to get the equivalent decimal version. So if I had 105%, I imagine my decimal point right here, I move 2 spots to the left, so I get 1.05. This is the decimal version of 105%. So 105% of the amount I initially borrowed must be equal to the amount I owe, $1,365. Now we have a simple linear equation involving X. So we don't know what X is, but we do know what 1.05 times X is. So to work backwards, we divide. We take $1,365. We divide by 1.05. So if this equation is true, that means this equation must be true. And that would tell us that we borrowed $1,300. Okay, and we could always check this, right? Start with this amount, tack on 5%. Find 5% of 1,300. To find 5% of 1,300, we would do 0.05 times 1,300. Okay? 0.05 times 1,300, if we crunch the numbers, is going to be 65. So, if you borrow $1,300, you have to pay back all $1,300 plus 5% of this, which amounts to $65. In other words, you have to pay back $1,365. Okay? So, our first example of an application of a linear equation. All right, let's do another one. Okay, so in triangle ABC, angle B is 5 times as large as angle A. Okay, so angle B is the bigger angle by a factor of 5. And it's a triangle, so they're going to give us 3 angles. Angle C is 2 less than angle A. Okay, so I'll draw myself a little picture here. Triangle ABC. Now, in the statement of the problem, they related angle B to angle A. There's a relationship between angle B and angle A. Now, I don't know what angle B is yet, and I don't know what angle A is yet. But let's say A was 10 degrees. If A was 10 degrees, B must be 50 degrees, right? Because it says 5 times as large. So the relationship is whatever angle A is, you multiply it by 5, and then you get angle B. Now, angle C was also related to angle A. They said C was 2 less than angle A. That means you start with the measurement of angle A. You take away 2, and then you get C. So to get C, you do whatever A is minus 2. Okay, you start with A, and then you go 2 less. All right, so I got this. Now I also know from general knowledge about geometry, A plus B plus C has to be equal to 180. Now right now there's too many variables in that equation, there's too many combinations. If I'm just allowed to pick A, B, and C willy-nilly, I can never figure this out. There's too many things that will work. However, the statement of this problem says I can't pick things willy-nilly. Once I've figured out angle A, I have to take 5 times that, and that's what angle B has to be. So, I can use that information to replace B with an expression that involves A. And I can replace C with an expression that involves A. So if I have everything in terms of one variable, now I can solve. That's the point. Okay? So, combine like terms here. 7A equals 182, right? Because that's A plus 5A, we're up to 6A. Got one more copy of A, so that's 7 total copies of A on the left-hand side. This doesn't have an A. I'm solving for angle A. I want to get rid of that. So I move that over. And then I would divide. So 182 divided by 7. Crunch the numbers on that, you will get 26. Okay? So, we know that angle A is 26. Okay, so if this equation is true, that means this equation is true, which means A is 26. Now, if we know angle A, we can multiply that by 5 and get angle B. If we know that angle A is 26 degrees, then angle B, let's see, 5 times 26. 5 times 20 is 100. 5 times 6 is 30, so angle B must be 130. And finally, this says that if we know A, we can back off by 2, and that'll give us C. So C must be 24. Okay, so we have all the measurements of all the angles using the fact that there's a relationship between angle A, B, and C, and they fit into this equation. The sum of all the angles in a triangle is 180 degrees, sort of a basic fact from geometry that we probably all knew. Okay, let's do one or two more. I've got some guys picked out here. Okay, there was one about air resistance I wanted to do here. Oh, okay. Here's a nice one. I've got this one marked. Okay. In 2013, IBM got 2,133 more patents than Samsung. Okay, so there's a relationship between the number of IBM patents and the number of Samsung patents. Together, they got 11,485 patents. So IBM and Samsung together got 11,485 patents. And the question is asking, how many patents did each one get? Okay, so I kind of think of it like this. Let me let I, capital I, stand for the number of IBM patents. And the capital S, that'll stand for the number of Samsung patents. Okay? So I know that the number of IBM patents plus the number of Samsung patents is 11,485. Now, as it stands right now, this cannot be solved. I've got one equation but two unknowns. We have to express this in terms of a single unknown. And here's the key right here. This tells us how the number of IBM patents is related to the number of Samsung patents. It tells me that to get the number of Samsung patents, to get the number of IBM patents, I take the number of Samsung patents and add 2133. So that I can be replaced by Samsung patents plus 2133. So we replace I with an expression that involves S. Now, don't forget this S is hanging around here. We replace the I with S plus 2133, but this is just sitting here. 11,485. Okay, so if that's true, let me go up here. I've got two S combining like terms on the left. I've got an S, I've got another S, so I've got two S's. What I'm going to do is I'm going to take this away from both sides. I'm going to take away 2133. So I'm getting 9,352. So I would take this and divide both sides by 2, getting 4,676. Okay? So this is the number of Samsung patents. And we know that to get the number of IBM patents, you take the number of Samsung patents and you add 2133. And that gives us a total of 6,809. Patents for IBM, okay? So this fits the conditions right there. So notice there's a relationship between IBM patents and Samsung patents. If you know the Samsung patents, you know the number of IBM patents. So we don't really have two distinct variables. The number of IBM patents depends on the number of Samsung patents. That's how we could do this replacement here. And if you're going to solve an equation, if you're going to solve a linear equation, it has to be in terms of just one variable. There's too many combinations if I have two variables, right? If all I know is two numbers add up to 11,485, well, I can't really figure anything out. But now, okay, if I know this number is 2,133 more than this other one, everything's expressed in terms of this number, the number of Samsung patents. And now I can go ahead and solve it. Okay, so that's the basic strategy. Look in the statement of the problem for relationships between quantities and try to put those into an equation and try to get that equation in terms of just one variable. And then once that's done, solve the equation. So getting the answer from here, well, that's the easy part. The tough part of a word problem is figuring out what equation to write. Okay, that's the challenge. So there'll be plenty of practice problems that give you a realistic scenario and ask you to answer a question. And the best strategy is solve an equation. Okay, write down an equation and solve that equation.